Check one, two. Check one, two.
Hey, excellent. Thank you very much. Well, yeah, we'll go through that at lunch and figure it out. So, yeah, sounds good. We'll give it another 2 minutes and we'll get started.
Make sure this works like it's supposed to.
Just going to give it another 2 minutes, guys. Or three, yeah. It's, but we were talking all morning. It's such a cool talk. I don't want to cut any time from it. So I figure my introduction. Oh, I can do my introduction at 11:09 and then get the talk started at 11:10.
So Brian, you're going to introduce
Yes.
Aaron and also moderate the questions?
Yes.
Okay, yeah, just let me know if you need any help.
Got it. Thank you.
Oh, there it works now. Of course, once I say something.
But he's still filtering in from other things. Hey.
Hey, good to see you.
Okay, it's 11:09. We're technically starting at 11:10, but I'm going to do my brief introduction now because I don't want to take any time from his very cool talk. So it's my great pleasure to introduce Aaron Donahue. I know he knows a number of you. I actually first met Aaron at a CESM workshop a couple of years ago when he was presenting a poster on some process reordering and the effects of that, which actually ended up being part of Monica's chapter in her PhD. And he's always working on really cool things, and Scream is no exception. And I'm thrilled to have him here today. I've been learning a lot from talking to him this morning already, and I look forward to this presentation. And on that note, all yours.
All right, so I should be good. All right, hello everyone. Thank you very much, Brian. Thank you for inviting me. It's always a pleasure to come to NCAR. I'm always impressed by how beautiful it is. It's like I sometimes always forget and then I come here. So I appreciate coming here and giving me an opportunity to talk about work we're doing at the DOE on our global climate resolving atmospheric model and running it on exascale computers. So as you can see just from the author list, this is a rather impressive effort by a lot of people. So I'm presenting on a lot of work that's not just my own, but also the work of others that I have the pleasure of working with. So the first big question I want to answer is why global storm resolving models and why now? So we have our workhorse models that run 100 kilometers, 25 kilometer global resolution. And here in this effort, we're pushing that to the extreme, going to kilometer scale models. So 3.25 kilometers now, but pushing it even past that in the future. And so the basic answer is that by going to that higher resolution, we just get access to more accuracy and the ability to capture things like extreme events, which is illustrated here in this atmospheric river video. This is from one of the Scream simulations, and this is an atmospheric river making landfall, of course, over California. Additionally, poorly parameterized subscale physical processes, they limit the predictability that we have for some of the global scale changes that we want to investigate. And so going to these higher scales allows us to then also answer those types of questions. And lastly, we're moving into an era of exascale computing, and exascale computers require a huge amount of work. And so these global storm resolving models can meet that demand, essentially. And so then the other question, of course, is why exascale computing? Other than the obvious that that's sort of where things are going, and we're making these bigger computers at the DOE that can handle exascale computing. But they sort of go hand in glove. With exascale computing gives us the opportunity to go to these higher scales. And so here we're looking at a diagram of just the sort of a gradation in scale going from 200 kilometer resolution, this is over California, all the way up to 1 kilometer. And we can see that 25 kilometers, one of our workhorse models, does actually do a pretty good job of capturing a lot of those topographic features. But when we go to kilometer scale modeling, we really do capture those topographic features, which gives us an opportunity to then really ask interesting science questions. GCRMs are incredibly expensive, and they typically run on some of the world's largest computers, but the beauty of that is that that expense is actually a boon when we're looking to use exascale computers. So that is another motivation behind the Scream project now. And I'll go into more detail on what that is. But first, I just want to talk about how Scream sort of came into being and where we are in our current timeline. So Peter Caldwell, who's the main PI on the project, is fond of saying that we were able to accomplish a full rewrite of the atmosphere model in C++ with just 4 FTEs in about 4 years. And the way we were able to do that kind of followed this timeline. And so first and foremost, we understood that although we wanted to rewrite the code so that we could take advantage of exascale computing, we also had to do a lot of the science preliminary, like right up front, in order to understand whether or not the model that we were creating was in fact valid. And so we broke the tasks into 2 pieces. We have what we call Scream v0, which is just an extension of E3SM using the Fortran versions of the code. But in this case, we developed the parameterizations, the processes that we wanted to use in our high-resolution version of the model. We developed them in Fortran, and then we were able to test them using existing infrastructure. So we were able to hit the ground running immediately on just understanding whether or not the processes that we were going to use were in fact valid and what kind of tuning we might expect. And in parallel, we had a team that was rewriting the atmosphere component of E3SM into what we call EMAXX, which was a complete rewrite in C++ Cocos. And so following this timeline, the Fortran we were able to run at high resolution and produce the V0 overview paper, which came out in November of 2021. And early this year, in the spring of this year, we finished, I know it says December 2022, but they took a while. We finished our first set of V1 runs using the C++ code, 4 different seasons, 40 days each, using the high resolution. We also, in July, ran a series of simulations just looking at performance, and those simulations were submitted as a Gordon Bell Prize, and we've been chosen for finalists, and so we're very excited to see what happens next week at supercomputing. In terms of what's going on now, we are currently running a set of CES-style simulations with that same version of the code, so 2 13-month simulations. And we have plans to start next year full-on decadal runs, similarly with the high resolution. And moving further into the future, we're looking at fully coupled runs. So it's important to note that all the simulations I mentioned so far are atmosphere-only type simulations. And so it's going to be about 2025 when we're looking at fully coupled runs. So I've mentioned this acronym, Brian mentioned it as well, SCREAM, which stands for the Simple Cloud Resolving E3SM Atmosphere Model. And what exactly is SCREAM? So it's an important distinction that SCREAM is not the model. SCREAM is the configuration. So SCREAM is the configuration of the model that is meant to work with 3-kilometer resolution and finer. And so I'll go into a lot more detail of what exactly is in SCREAM in later slides, but I just want to make sure that this acronym is understood because I'm going to use it throughout the talk, and it's good to know. And so SCREAM actually has 4 different configurations. There's the global kilometer scale atmospheric configuration, which I'm mentioning down here. That one is currently basically done. That's the configuration we're using for all the simulations I just mentioned. We also have a regionally refined capability and a doubly periodic capability. I'll talk about the doubly periodic a little later on. These are capabilities that are currently implemented in the Fortran, and we're currently porting it over to the new C++ framework. And then there's the coupled kilometer scale, and that's basically a mention to the 2025 proposed simulations where we're running our kilometer scale in C++, but we're running in a fully coupled configuration. And this figure here essentially demonstrates that the SCREAM configuration does do a very good job of representing some of these extreme events. And so here we're looking at comparisons between satellite data and SCREAM v1 simulations at different locations in the globe, and we can see just from the eyeball norm that SCREAM does a particularly good job. And so what is EMAXX? This is the other acronym I keep referring to. EMAXX is that C++ implementation of the E3SM atmosphere model. And so it essentially is just the E3SM atmosphere model in the new infrastructure with C++. We also use Cocos, which I'll talk a little bit about in a moment. And Cocos gives us capability to have performance portability and hierarchical parallelism, which is essential for taking advantage of these exascale machines that we're running on. And why do we go to C++ EMAXX? And this is actually a question that we get often, and it's totally a fair question. So why rewrite the whole model in a fully new language? Well, first and foremost, in order to take advantage of the DOE machines, we need GPU usage. And while it's true that you can take advantage of GPUs with Fortran code, it is simpler and more straightforward to do it with C++, especially when you consider using C++ Cocos, which is essentially designed for taking an existing code and porting it to a new machine quickly. And so that was one of our major motivating factors. Also, legacy code was hampering our development overall. So those of you who might be familiar with using the code, and I don't know if you know this, but I mean, many of you do, E3SM and CESM share a lot of similarity. And there's actually quite a lot of CESM code still existing in E3SM. And that legacy code can sometimes crop up when you least expect it and make it difficult to make nimble changes to the code. Some of you may have experienced that, and we were experiencing that as well. And considering what kind of undertaking this was, it made sense to really consider how can we abandon some of that legacy code and kind of get a full rewrite from the ground up, focused entirely on running at Exascale. So the status is that the kilometer scale is operational. We don't have a low resolution, but that is planned. And so sometime in 2026, we expect to have a low resolution version of the model. And what I mean by low resolution is one that has a physics package that would be amenable to running at 100 kilometer or 25 kilometer. And so that's really going to require us to take the deep convection scheme and the gravity wave scheme and port that also into C++. So it's actually part of the EMXX framework. And similarly, we are currently developing a lot of tools. I've already mentioned these, like doubly periodic, diagnostic suites. And so those are being continuously built. So some of those are online now, and some of those are still under development. And so now that I've sort of discussed, broadly speaking, the project that I wanted to discuss in this seminar, I'll just give you a brief outline of what I'm going to talk about. So the focus of this talk will predominantly be on our computational strategy and the performance that are related to that. And that's mostly because that's my expertise, so I feel most comfortable talking about that. But I also will talk a little bit about the screen results from our latest runs, the ones that I've already discussed. So jumping right in to talk about computational strategy and performance, as I mentioned, EMXX is a complete rewrite, which gave us the opportunity to really think about how would you develop a model if you started now rather than a model that you've inherited over the last few decades. And so one of the big things that we wanted to place into the model was flexibility. And so this diagram down in the lower left-hand corner, let's see if my pointer shows up. Oh, sorry, that's my pointer. So down here in the lower left-hand corner, this might actually be familiar to a lot of you, this idea, this schematic of sort of like, how does the atmospheric model sort of communicate with the rest of the global model, right? The ocean, et cetera. And then how do we sort of move data around? And that's this concept of an atmospheric driver, right? Which is really the brainchild of the whole atmosphere model. And as you can see, if we consider all the different moving parts, we have fluxes that are imported and exported. This is the main way the atmosphere communicates with the rest of the Earth model or system. And then we have what's going on inside the atmospheric time stepping. So we have physics and dynamics and input and output. All of that is fed through the atmospheric driver, and it does the most of the organization. And that's currently the case also in the Fortran version of E3SM. Although, if we were to write probably this same schematic for the current Fortran implementation, there might be some crossed wires and things kind of going all over the place. There is a lot of dependence, for example, between the different physics parameterizations, which does make it less nimble. And so in order to sort of address that concern, making things more nimble, we decided to take advantage of C++ and object-oriented programming. And so we've created an atmospheric driver that sees all of these processes as simple objects of a general class. So we've created this atmospheric process class. And so from the driver's perspective, it doesn't know it's talking to macrophysics or microphysics or radiation. It knows it's talking to the process that's currently occurring now. And so we have a general interface that can be defined based on the process that you're working with, but from the driver's perspective is in fact general. And then we have a process representation, which is deeper down. And this is really the main brain code. And the idea is the interface is its own CPP. It's its own file that you would then generate. And it would call the actual parameterization. And so the idea being that when someone comes with a new parameterization, they have their standalone parameterization. And all that's necessary in order to put that into EMXX is the generation of that interface and make sure that all the wires are connected the way they're supposed to. This is a very similar idea to an ongoing effort that's going on with NRL and NCAR and NOAA, which would be the CCP MCP, this idea that wouldn't it be nice if it was a lot easier to plug and play with our parameterization. So we wanted to build that into EMXX as well. Another really strong benefit, which I'll discuss a little bit in the next slide, that comes from this approach is unit testing. And so one thing that we really wanted to do was test this code robustly. And by making all of the processes their own little contained object, that also allowed them to be independent from the rest of the infrastructure, which gave us this ability to do more robust unit testing. Lastly, I'll state that a big conversation that we had was how do we sort of address the the intersection of fizz state, fizz10, and pbuff, these are all three words that you'll know if you've ever had to code in CESM or E3SM. How do we marry those together and make something that's a little bit more streamlined? And what we came up with was the field manager, which is essentially all three combined into one. And one of the big parts of that is that pbuff was very opaque. You could definitely add stuff to pbuff and get stuff out of pbuff, but it wasn't always clear where stuff was being added, right? Pbuff is kind of this very useful structure, but also very opaque. And so we wanted to address that. So we came up with a field manager. And what essentially it is any information that needs to be passed from one process to another is registered with a field manager. And again, we take advantage of object-oriented programming. We have fields, and fields have metadata, they have structure, and they have pointers to actual data, and those objects are passed around. And so that allows processes, for example, they can request not only for a field, but they can request the units. And this is really useful, for example, I/O. I/O is able to determine the units just by looking at the field, and if that field gets changed in the code elsewhere, that will automatically be updated in the I/O as well because the metadata travels with the data, which we've found to be very valuable. And so I talked about unit testing, and now I just want to go in a little bit more detail about that. So we wanted to make sure that our code was robustly tested. And this is really just a software engineering best practice, right? And it's difficult in legacy code because a lot of the testing infrastructure needs to work also with how that code was developed at the time. And what we found with E3SM is that a lot of the processes that we would have wanted to test on a very elemental level were dependent on the greater E3SM code, requiring our tests to also build all of E3SM, maybe just to make sure that if we change one number that we see the change elsewhere where we would expect it to be. So it was very clunky. But by switching to this object-oriented approach, we were able to then put together unit tests that could really just zone in on one specific task. And it allowed us really to just have a lot of unit tests. And so that's kind of illustrated by these 3 points. And so the first one I want to bring your attention to is in the lower left-hand corner. And this is just like a screenshot from running all of our unit tests in the code. And these can be run manually. They can be run on a single node. We have about 276 currently, and they just go through all of the code, and they run, some of them run very simple things like, is 2 + 2 = 4? Not that basic, but on that same level of basic, and some of them go through more complex questions. But essentially, they're really just making sure that if you make a change to the code, do you break anything? Do you break anything where you might not expect it to be broken? And that's why you can run the full suite. You can also run these manually by just one at a time. So if you're only working in the macro physics, for example, you can run all of the code, all the tests that touch macro physics and make sure you didn't break any of those. And so this really has made our development quick and nimble. And it also has made it less bugs have creeped into the code, as it were. This unit testing is actually integrated directly into GitHub. So whenever someone requests a PR that they want to have merged, it is run through an auto tester, which immediately runs all of these unit tests on a couple of machines. One is GPU machine, one's a CPU machine, so we can test whether or not you've broken GPUs but not CPUs, et cetera. And code doesn't get integrated unless it passes this, or if an administrator goes in with a hammer and forces it through. And that happens occasionally, but there's only a couple of us. So you gotta make a really good case. And essentially, there's another layer of protection. And then lastly, we have a much more robust set of nightly tests that are run every evening and reported to this dashboard. CDash is the name of the dashboard. And every morning, it's actually me who does the checking, goes in and checks and makes sure that we don't have, like in this case, some new fails. And if there are, then I start contacting people and trying to figure out why. But again, just another layer of protection to make sure that bugs don't get too far down into the code and start impacting our science runs. So robust testing is something we're really proud of, and we advocate, we sort of preach to everybody if you can pull it off. So computational strategy, I mentioned Cocos before. So Cocos is a library that's meant for performance portability. It's essentially a wrapper for all of your parallel coding that under the hood will make sure the compiler compiles all of your code appropriately, be it if you are on CUDA or AMD or any of these new machines. Cocos is supported by Sandia. They've got their whole team of their own thing. They're not necessarily related to our code alone. So they support Cocos. They also make sure that a lot of Cocos stuff gets into C++ standards, so that's also very valuable. But one of the big things is that when a new machine comes online, Cocos gets to go in there and make sure that any code that uses Cocos should, out of the box, hopefully, be able to run on the new machine as well. That's of course not always the case, but we are like 90% of the way there when we move to a new machine. For example, when we moved to Frontier, we were already a big chunk of the way towards getting our code running on Frontier. There were some little things we had to tweak, but that's always the case and kind of unavoidable. So this is exactly what that kind of looks like. So here's a parallel for loop, and you can see in the highlighted section, this is where Cocos kind of jumps in. And so it essentially is just a wrapper. So here we have a parallel reduce, and there are some aspects of Cocos that there's just the language, like what is a team thread range and stuff like that. But that's essentially what it is. And so all of our parallel loops utilize Cocos. Cocos is by no means the only one. Lawrence Livermore has a product called Raja. Oak Ridge has a product called Yackle. So there are other alternatives, but they're all essentially the same idea. Performance portable libraries that allow you to just move from machine to machine and still get the same performance. There's a downside though, and some of you might also have this experience as well. Going to C++ as we did can be a lot more complicated, maybe always is more complicated. I don't know if I want to be so bold as insane. But if we take that same chunk of code I just showed you and we looked at what the original Fortran would have been, it's pretty clear that that is a simpler section of code. And actually maybe even more readable compared to what's going on here. This is a concern of ours, and we're not quite sure what that's going to look like because we're still the only developers on the code. And when it gets released, we'll have more experience seeing what happens when new developers have access to the code to start working there. Our hope is that it's not going to be the case that only software engineers are the people that can actually code in this model. And that although there is a steep learning curve, I can say for myself that when I started this project, I was only a Fortran modeler. And now I feel very comfortable programming in C++ Cocos. Hopefully that same experience is the same for those of us who have to adopt it new when it becomes the release model. I will note, though, that we just gave us the opportunity to remove a lot of outdated stuff by rewriting our code from scratch. And lastly, a lot of this complexity does actually come from this construct that we introduced called packs. For those of you who might be familiar with chunks in the physics part of CESM and E3SM, this is kind of a similar idea. It's an effort to allow us to do vectorization on CPUs so we can still utilize CPUs at their max performance. But packs do introduce a lot of complexity. And that's a lot of what you're actually seeing in this complex code. So was Cocos a good choice? We think so. We're pretty happy with it, although we're also cognizant of the fact that it's new and it might be difficult for new scientists to take on. It does allow us to run on any architecture, past or future, which is fantastic. And we have found that C++ compilers and tools are better supported by vendors. It's true that Fortran is as well, but it has been the case that C++ compilers might get a little bit more attention first. It does have broad and enduring support, which is a big boon to Cocos. And really, just for personal reasons, a lot of the people that signed on to this project are Cocos experts. They were part of the task of porting home, the home die core to home XX, the Cocos C++ version. And so that expertise meant that we were able to really start in a strong hand and get going really quickly. And they were able to help us non-Cocos people much more in the beginning, much better. But the experiment is still ongoing, and so there is a fundamentally different relationship now that we're going into C++ Cocos, and we will see what that looks like as the model evolves. Although I will say, and some of you may be familiar with the Omega XX project, the Ocean group for E3SM is now moving towards a similar templated programming approach, although they're using Yackle instead of Cocos. Also worth mentioning that a lot of other groups are looking at GPU porting, and by no means is Cocos and Yackle the only way. For example, you could use Julia with a GPU backend, Fortran code, as what NICAM is doing. So it isn't the only way, and it's just important to think about that as well. Now, the really fun stuff, how does it work when it comes to performance portability? So the first thing I want to show you is a 1-degree simulation, so 100 kilometers. So this is going back towards the coarser resolution, and it allowed us to really look at the difference between CPUs and GPUs. And so this figure on the right shows the comparison between CPUs and GPUs. There are not CPUs and GPUs. I meant to say Fortran and C++. So we have 2 Fortran codes, simulations, and then we have, roughly 6 simulations using the new C++. So the black lines are Fortran and all the colored lines are C++. And the main takeaway I want you to get from this figure is that moving to C++ did not represent a decrease in performance. In this case, we can see that it's about the same, Fortran versus C++. And in this case, we actually did a little bit better using our C++ code. And then, of course, we can see with the GPUs, we actually get a better performance overall. But I'm going to talk a little bit more about that in detail on the next slide. The main takeaway just is going to C++ wasn't a hindrance to our performance. Now, if we go up to the full 3-kilometer simulation, we can look at the performance overall. Now, one of our express goals was to hit 1 simulated year per day. And we're very excited to see that on our latest frontier runs, albeit a big significant portion of the machine, we were actually able to break that threshold and get to 1 simulated year per day. So here we're looking entirely at the C++ code, but now we're going to compare just GPUs versus CPUs. And in this case, we see that Perlmutter CPUs significantly underperformed the GPUs, which is what we would expect. Another big takeaway from this is that the same code base is being used for Perlmutter, Summit, and Frontier. And so we were essentially able to pack up this code and move to these new machines and get running pretty quickly. And that's just a big testament to that performance portability and the benefit of that. And then, of course, just top line, we're very excited to see this 1 simulated year per day on Frontier. So next, I'm going to tunnel down into looking at just the process level performance and discuss whether or not there's any way that we can further improve our performance from what we just saw. And so if we look at just on a full atmospheric time step basis, we can just kind of look and see where we're spending most of our time. And of course, the big takeaway is that the die core is a significant portion of the overall atmospheric time step. Another big takeaway is that microphysics and turbulence are not. And one of the reasons why is because we switched to the PG2 mesh. You can see a paper by Walter Hanna, one of my colleagues, that goes into more detail about that. But that actually made a significant improvement in our overall performance for microphysics and turbulence. Radiation currently is not load balanced as it is in E3SM, the Fortran version, the CESM. So there might be some improvement that we can gain from that. The die core, unfortunately, that's where we would want to get the most amount of improvement, but it's also the most optimized version of the code, going back to the HomeX export where they did spend a lot of time optimizing it. And lastly, we have output. We spend a significant amount of time in output, and that is actually maybe a low-hanging fruit. We are looking at using Audios as a way to improve performance, and in the next slide, I'll discuss another way we might be able to improve that performance. So this is kind of just big picture one way that we might be able to improve overall performance. And really that's just taking advantage of the fact that most of the atmosphere is run on the GPU, which leaves the CPU idle during most of that time. And so those idle CPUs could be utilized for something. And so one possibility is just to give those over to the ocean and run the ocean in parallel with the atmosphere and let the ocean take advantage of all that CPU power and improve our overall run time that way. Another way, and it's not really illustrated here, but we could also do that, would be to unload I/O onto CPUs. Actually, it is on CPUs, but allow the I/O to work in parallel with the GPUs running the atmosphere model and hopefully significantly reduce some of that I/O cost. And so this is just a sort of low-hanging fruit that we haven't yet had an opportunity to exercise yet, but is something we're looking at for improving our overall performance. There are a few other ideas. So for example, single versus mixed precision. We could put radiation on a coarser grid. It's currently also running on the 3-kilometer grid. And then better load balancing I already mentioned. And another project that I'm working on that I'm not going to discuss in this meeting, but I'm happy to talk about with others after the seminar, is using machine learning to emulate the global storm resolving model. And there's some work we're doing with Chris Betherton at AI2 on doing exactly this with the screen model. And that's there's a sort of a demonstration of how we don't actually see a significant decrease in the overall error, and this is from Chris Betherton. Another big challenge going to these 3-kilometer models is just data. As you can imagine, we have a lot of data because we have increased the number of columns by orders of magnitude. And that's very well illustrated in this figure here, where if we consider the entire CMIP5 archive and the entire CMIP6 archive, so a lot of data, and we look at this blue line, as we simulate Scream, let's go out to somewhere around 22 years, we've overtaken the entire CMIP archive in terms of storage. So that's a big deal. So where you store it, how you access that data, is another big challenge that we're looking at. And so some of the solutions we've been considering and are actually employing currently would be regional output. So either just outputting at specific observation sites where we care about, or just in certain regions where we care, or just coursed output, where we do a 3-kilometer resolution, but the output is just written on a 25-kilometer domain. Depends on the kinds of analysis we want to do with that output. Data compression is another, changing the amount of subsampling we do for temporally. Or just computing statistics online. And so I think these are all things that we've thought about even with our coarser resolution models, because data is always kind of an issue. But as we move into 3-kilometer resolution, it becomes a sort of like existential crisis when we start thinking about running for decadal runs. And so it's something that I think becomes a much more pressing problem that we do have to actually address. Another data style issue is just sharing that output. So we have a lot of output, and how do we share it? We want to minimize our data movement, obviously. We currently store data on NERSC, so people who have access to NERSC would also have access to our data. But there's no special archives that we can particularly use. And so another thing we're looking at is how do, and this is actually maybe more broadly for the full community, as we go to these higher resolution models, as we produce tons of data, how do we share that data for science? I don't have an answer for you, but I think it's important to bring up in this context that this is something that we're going to have to think about. Oh, yeah. So that was computational strategy and performance. Now I'm just going to briefly touch upon some of the fun results. I mean, it's exciting to run these models and to see what the results look like. So the last couple of slides, I'll discuss those. So I'm going to go back and just say, like, what is Scream? So I've been talking about Scream as this model, but I haven't really gone into detail on exactly what's in it. And so that's illustrated by this schematic. And so Scream is simple. That's the first letter of the acronym, right? And so we've simplified it dramatically. So we have a single turbulence scheme. That's shock. Aerosols are actually prescribed, although there is a separate project that's working on prognostic aerosols that could be put into the model. Fluid dynamics is the spectral element dicore, the home XX dicore, non-hydrostatic. Microphysics processes are handled by P3, but a simplified version of P3. We only have a single ice category. And radiation is handled by RRT-MGP. That's it. So if any of you are familiar with the physics package in CESM and E3SM, there's quite a bit more than that in our typical model. But Scream is really just those. We also have a series of useful tools that we use with Scream. First and foremost, this doubly periodic mode has been proven to be very valuable. And there's a reference here if you want to learn more about that. It's been recently published in James. But essentially, a doubly periodic is kind of like an extension of the single column model. At our 3 kilometers, single column model is no longer a valid tool for us to do the kinds of analysis we were doing with it at 100 kilometers. And so the solution then is instead a doubly periodic version. And so what happens is we create a domain of Scream, and it's doubly periodic, exactly like it sounds. So if you look at this video that's happening on the right-hand side, you can see that, of course, as clouds move off this edge, they come back on this boundary. So it's a doubly periodic domain. And what we do is we superimpose a single column at every column of that domain, and we can plug in how much resolution we want. So we can go to even like 100-meter resolution if we want to. It's completely independent of like the grid for Scream, for example. We superimpose a column on all of the columns, and then we do a mild perturbation, and then we allow the solution to evolve. And this has allowed us to look for scientific issues in some of our parameterizations, do very rudimentary or very like simple testing on them. And we're looking at ways to use doubly periodic Scream for more of our analysis and for more of our testing. So it's a really powerful tool. Scream can also run in regionally refined mode, which is, of course, helpful from the perspective of performance. So it allows us then to run at our 3-kilometer mesh, but of course for longer periods of time when we want to. And we currently have COSP implemented, albeit in Fortran, not in C++. So we use a Fortran C++ bridge. Future evaluation that was ongoing and we're looking at is taking the data that we have. And as I already mentioned, doing output directly on global observation sites, and then looking at those results. And so we're partnering with the ARM program through a project called Thread, which is headed up by Yang, who is one of my colleagues at Lawrence Livermore, where we're going through the Scream data and using that Scream data to do this comparison with ARM data, which is also fantastic. So just some of the good stuff from Scream. So some benefits of Scream is that it does solve a lot of our long-standing problems with the E3SM model. It does a good job of capturing storm structures, so tropical cyclones, atmospheric rivers, precip intensity. So if you're looking at the figure on the right, it's a comparison between GPM and Scream V1 precip intensity, and we can see it's actually a very good agreement. And we also capture the diurnal cycle very well. And low clouds are much better in Scream than they are, and this might be because of the implementation of shock. But Scream is also a young model, and there's still a lot of work to do, and so there are some growing pains. And so here we're looking at a comparison of Scream data with the Southern Great Plains site, and we can see that the dashed lines. It's kind of hard to read the key because there's so much going on here. But the dashed lines are the model, and the solid lines are the data. And we can see that in some cases, there is quite a lot of bias between the model and the data, right? So we see things like the 2 meter temperature is too high, particularly at night, or that the 10 meter wind is too high, maybe due to a lack of mountain stress. And we see here that the liquid water path may be too low, and it's unclear whether or not we can tune it. Now, we have been working on these problems, and so these figures are a little outdated. We think we might have actually addressed both of these issues. We implemented a turbulent mountain stress parameterization, so that was not on my original schematic, but is now part of our new runs. We may have fixed this with changing the way the boundary layer is handled in shock. And so we're hopeful that we will see some improvement here, and maybe some tuning can help that as well. We currently have a set of simulations just looking at these two changes to see how much of an impact they have on these errors. Now, the last thing I want to show you in terms of Scream results is kind of our white whale, as it were, is popcorn convection. The last time I was here in Boulder was last year at the WCRP conference, and I was talking about popcorn convection then, and I'm still talking about it now. We are having a lot of trouble trying to figure out what is causing this. And so popcorn convection is this phenomenon where we see convective systems pop in and out of existence as the model evolves in time. And so we've been really just trying to figure out what it is. We have some ideas, and we did some recent improvements to the model, and we're going to be able to look at the analysis of those results soon and see how much of an impact that had on popcorn convection. But this is kind of an outstanding problem, and as we're saying, this is not a problem only to Scream. A lot of the kilometer scale models are experiencing similar kinds of phenomena, and so it's kind of just a big open problem that we ourselves are definitely interested in. So just some parting thoughts. Pervasive unit testing is one of the biggest improvements we feel in Emacs. So we're just going to continue to preach that unit testing has been, invaluable to our development, and we think it's a really good thing to do if you have the opportunity to. The evaluation site data has been a big boom for us because we've been able to look directly at ARM results, and just like I showed in sort of our growing pains slide, it's been able to us to really focus in on deficiencies in our model and then try to figure out where those deficiencies come from. Cocos isn't magic, it's a tool. It does provide performance portability, but there are other tools as well. And characterizing the predictive uncertainty of global storm resolving models is really just a grand challenge for the community. In summary, Emacs, which I talked about a lot today, is the new the C++ configuration, or the new C++ version of the E3SM atmosphere model, and Scream is the 3-kilometer configuration. It's operational, but is rapidly improving. We have a lot of capability in there that we are excited about. We are currently working on the C++ regional refined modeling implementation and the C++ doubly periodic. And once we do that, we are going to abandon the Fortran code, and we are only going to develop the C++. And in the future, the C++ it will be the only version of the atmosphere, or the supported version of the atmosphere model for E3SM. We achieved our long-standing goal of getting 1 simulated year per day on Frontier. And we have a series of simulation plans slated for the future. We're right now doing 1-year simulations with +4K sea surface temperature increase and a control run, so sestile simulations. Next year, we're going to start decadal simulations, similarly, a control and an altered run. And we're looking at doing coupled simulations too, and so that'll be a big jump forward. And Scream just accurately captures CloudStorm behavior, but it still has some deficiencies that we're trying to address. And lastly, I just want to shout out that this is not a project that only a few of us worked on. This is a huge project. It takes a village to raise a portable, performance portable model. And so these are all of the collaborators from all the different enterprises, labs, national labs, private industry, University of California. And so I do want to say that their contribution, all of them, was integral for us to get this far. And of course, the ongoing effort is valued. And so I will leave you with this beautiful video. I have to have one of those. This is, of course, a Scream run. Long wave flux up at the top of the model. And I would welcome any questions. Thank you.
Thank you. Any questions? Oh, yeah. Multiple right off the bat.
Right off the bat.
John Dennis. Yeah. You were quick on the draw with your hand, so yeah.
Thank you for the talk. One of the questions I had, and I might come up with more afterwards, you said you're going to abandon the Fortran 90 code. How do you get scientists and others to abandon their contributions?
That's a great question. So maybe I was actually too strong. Probably someone watching on YouTube is probably yelling at the screen. I don't think we're going to abandon the Fortran code. We're going to stop supporting the Fortran version of Scream. So this Fortran code will still exist. E3SM v2, for example, is in Fortran and will exist and will be supported. I don't know for how long, because that's kind of outside of my pay grade, as it were. That's more of like a leadership decision. But from the Scream perspective, we have been supporting the Fortran version of the Scream physics. That would be the P3 implementation and the shock implementation that we put into the code. And so far, whenever we've made advancements to shock and P3 in the C++ version, we've had to update the Fortran version so that we can maintain bit-for-bit capabilities, because that's part of our robust unit testing. That's part of our testing, is just make sure the Fortran and the C++ agree. But once we are able to, we'll just stop supporting the Fortran version. Now, the broader question I think you asked is, at some point, the C++ version will be the atmosphere model in E3SM, and there will be a push for new development to be in C++ Cocos. And that's a bigger question. And that kind of alludes to my slide, like, is this a good idea? What's going to happen? And that's something we're still going to discover. We would make the point that you can still bridge Fortran and C++. So early development, if you have a Fortran code that you want to just see from a scientific perspective how it would perform in E3SM, you could still bridge it to Fortran, right? So it's not that you have to show up with a C++ model right out of the box. But in terms of supporting for like our release version of the model, because we have such an emphasis on being able to run an exascale and take advantage of GPUs, we're, I think, going to really put a lot of pressure on anything that's going to be in the release version of the model to be ported into C++ Cocos. And I don't know how that's going to go. I mean, the hopes is that it could work and that software developers will be able to make that transition, or there will be assistance for making that transition. But that's left to be seen.
And because I know it's somewhat related, I'm going to go to the online question. What wasn't clear what was done for the land model. Is it built in or coupled?
So it is coupled. That's a good question. It's the Fortran version. All of the rest of the Earth system and all these simulations is in the original Fortran. The land is coupled and is active. The ocean is prescribed in these simulations.
Thanks for a great talk. 2 questions. One, I think you said 4 years and 4 FTEs for the translation. Could you give a sense of the size of the code? How many lines of Fortran was ported? And then secondly, I think you started Scream about 4 years ago. If you were to start today, do you think you make the same choice, C++ Cocos, or might you look at something else?
That's a great question. So the 4 years, 4 FTEs is just really, it's like it could be on a banner. So it wasn't 4 people for 4 years. It was a lot of people charging, some people 80% of their time, 100% of their time, some people 20, 30% of their time. So, so yeah, that would be the scope of it. I was 100%, so I'm amongst the group that was like all about Scream, but we definitely had a number of software engineers who were 20, 30% on it, and so kind of come up to 4 FTEs. The Scream team itself is actually much larger than that. I think we have an order of 12 plus people. I mean, you saw that there were a lot of collaborators, but like the core team. But a number of those were scientists as well that were really just looking at like P3 and shock and developing those for the physics aspect of things. I think that answers your first question, right?
How many lines of code?
Oh, the lines of code. I wish I could tell you. I will say that I have guiltily looked at GitHub to see how many lines of code I've just like deleted versus how many I've added. And I will say that C++ is way more code than the Fortran. And that's clearly illustrated in that example that I gave, where the Fortran seemed much simpler. And so yeah, there is a lot more code from the perspective of individual porting things. There's a lot less code because we've gotten rid of so much legacy code. So there's a lot of like, for those, I'm going to shout like .f90 things at you, but those of you who are familiar with physpackage.f90 is a huge chunk of code. And if you were to think about what that's accomplishing, it's much less actually in our code. But that's just because there's a lot of legacy stuff taken out of there. There's a lot of stuff that we didn't have to port over. So yeah, I'd say just broadly speaking for that transition, yeah, if you're looking at Fortran code and you're trying to think about how much code that's going to be in C++, it's likely to be more and complicated. That's a much broader conversation because we're doing a lot of templating. So there's like a lot of abstraction in that as well. Was that? Oh, would I go back and do the same thing? That was the last question. So personally, yeah, because now I can program in C++ Cocos. And so I can't imagine having to transition to anything else. I think more broadly, just for like the benefit of the community, the experience, I do really appreciate the power that C++ brings. Like, as somebody who worked in the Fortran code, I think for 2 or 3 years before transitioning to this project and then working in the C++ code, I have found it very liberating. Once I understood what was happening, once I was able to code, I found it very liberating. The flexibility I had, the ability to really elegantly define the aspects of the code to their base properties, and then utilize that throughout the code. So I have really enjoyed like this atmospheric process class that we created. I've been in a lot of meetings with other scientists who have asked, can I do this? Can I do X, Y, Z? And the fact that we created this object-oriented approach allows me to say like, yes, we can do that. Like that's not going to be difficult. Whereas I feel like if I was back in the old Fortran code, I would have had to really think about like, how is that going to get in there? I mean, there's a lot of ifs, whether or not it's going to work. So I would certainly say from experience, that kind of approach to the programming, I feel has been very valuable. C++ Cocos, I think a lot of people would argue that you could do a different approach and it would be just as good. And that would be, they would be probably perfectly valid in saying that. I mean, you have to pick one, I think would be the important thing, and just commit. Otherwise, you can get kind of bogged down in the what ifs, but yeah.
Yeah, very interesting talk. You showed these bias plots between the observation and the model, and then you said you deal with the boundary layers somehow, and if you go to 3 kilometers and beyond that, you somehow start violating Molinovikov. What do you do with the boundary layer?
So I'm not going to be able to answer that because I am not an expert. So I'm not going to even pretend that I can get to the specific question you asked. I can tell you what we did. There was just a boundary layer treatment in shock that we discovered was not appropriate at these levels. And so Peter Bogenschutz, who wrote shock, investigated that thoroughly, figured it out, and made those changes to shock. Those changes were made after those results were simulated. And because it's such an expensive model to run, we couldn't just quickly go out and run it again to see if it worked. So we're just kind of like waiting for the simulations we have going now to kind of finish so we can see what that looks like. But in terms of the pure physics, I apologize, but my expertise was totally in the software engineering aspect of it and building the model, and I can't speak to like the actual turbulence.
Actually, I'm going to go to one online first. So Matt is asking, did the underlying process code require much refactoring to permit unit testing?
So you're talking about the C++, I'm going to assume. No, because when we designed it, we had in mind that we wanted to do unit testing. And so all those hooks are really arbitrary. So there is like, every process has an initialization, a run, and a finalization. And the arguments that go in are very simple, and the arguments that come out are very simple. So basically, every unit test just needs to build a field manager, create the process, and then do what you want to do with it. And the field manager itself is not so interleaved into the atmospheric driver. It's its own object. It's its own thing. So you can build a field manager on the fly, no problem, add stuff to it, take stuff away from it. So yeah, to that point, we designed the code in such a way that, yeah, the atmospheric processes were amenable to unit testing immediately.
Nice talk. You just answered the first of my two questions mostly. But just to follow up to the unit testing, does this infrastructure allow you to make sure that you check all the logic, like typical physics parameterization will have a lot of if this or that? Do you make sure you go through all those paths in the unit testing?
Yes, in the sense that we trust the developer to do that, yeah. So no, so it's not automated. I think, yeah, see, it was good. So I think we did have like a code coverage thing that we experimented with. I don't know how mature our code coverage checker is to make sure that that's actually the case, where you run the test and it makes sure that you've checked every line of code. You know, it sort of just says like, yeah, this line was checked at some point. We do have something like that. To be honest, I don't think that we rely on it as strongly, but maybe someone on my team would jump on the chat and tell me I'll like that is not correct. But we do, as sort of the gatekeepers of the code, constantly ask in our PRs, like, have you checked this conditional? Have you checked this conditional? So for our purposes now, it seems to work. But I could definitely see that cat getting out of the bag at some point, and it could be bad.
And then just quickly, you said that Cocos might be a feature of C++. What does that mean? Does it mean that it's
so
more
the C++
supported?
standards. So the C++, I don't know this very well either because I don't also do compilers, but my understanding is as they come up with new standards for C++, like I think we're at C++ 17 and maybe we're going to C++ 20. Don't. Thank you, Sean. Yeah, don't. I'm going to be embarrassed if I try it too hard. That Cocos is part of that conversation, and so things that Cocos, like Cocos, I don't know actually, to be honest, I can't frame it properly. But Cocos is a part of this conversation, so things that come out in the C++ standard also involve, you know, folks from Cocos either requesting those features or having some input on those features.
So getting to your science question about uncertainty quantification and predictability, I was wondering if the model had been built having data assimilation or other capabilities for predictability initialization in mind, and also what are you using to initialize the experiments that you showed us?
Yeah, that's great. That's a good question. So the first question, not now, but again, going back to sort of like the previous question that I was answering about how this, like, when someone asks me, can I do that? And I'm able to say pretty quickly, I think we can. For data assimilation, it's the same idea. The flexibility in the code, I believe, would allow us to you know, undertake that project without having to really rewrite a lot of the code. I think it would be able to assimilate that, to use a pun, easily. I mean, easily is the wrong sense, but I think there's a straightforward path to doing that. So I would say in the future, sure, but we're not doing that now. Initialization is your sort of classic E3SM run. We have an initialization file, like an initial condition file, that is then read in at initialization, and then the simulation is allowed to go from there.
And there were more questions, but it's noon, so I might say if you have more questions, come and join us at lunch. We can talk then, or later in the day. Aaron still has some other time free as well. So let's give a round of applause again. Thank Aaron for his time.